Discrete random variables can also be two other forms of random variables. So we've got our discrete random variable, and of that you can be classified as a binomial random variable or a geometric random variable. Since we loved probability units so much, we can also think of it as a Venn diagram, with our sample space being discrete random variables and our binomial and geometric random variables being a subset of that set. So we saw in a previous example that when tossing a coin 3 times, recording the number of heads obtained is a discrete random variable because the outcomes are numbers with gaps instead of an interval. So we're going to use the same scenario to differentiate between a binomial setting and a geometric setting. So an example of our binomial distribution is tossing a coin 15 times and recording the number of heads that occur. We're going to let capital X be the number of heads obtained. The probability of distribution of X is called a binomial distribution. A geometric distribution, on the other hand, looks like this. An example would be toss a coin as many times as necessary in order to obtain 15 heads. Let Y be the number of trials necessary to obtain 15 heads. The probability distribution of Y is a geometric distribution. Even though these two examples are very similar, there's a key concept that differentiates the two random variables, the number of trials. In a binomial setting, there's a fixed number of trials. In our example, the coin was tossed 15 times, a predetermined amount. In the geometric setting, the coin will be tossed as many times as necessary, an unfixed amount. In the binomial setting, the variable X is the number of successes, while the geometric setting, the variable Y is the number of trials necessary until a success occurs. Here's the criteria to determine whether a setting is binomial or geometric. For a binomial distribution, we use the acronym BINS. B stands for binary. So binary means there are two outcomes. Either the outcomes of each trial can be classified as a success or a failure. I stands for independent. Trials must be independent. Knowing the result of one trial must have no effect on the result of another trial. N stands for number. The number of trials, N, of the chance process must be fixed in advance. And S stands for success. On each trial, the probability P of success must be the same. For a geometric distribution, we use BITS as our acronym. B stands for binary, again, success or failure. I stands for independent, same idea, knowing the outcome of one trial will have no effect on the result of another trial. Except this time we use T for trials. The goal is to count the number of trials until the first success occurs. And lastly, success. On each trial, the probability P of success must be the same. So it's easy to remember that BINS goes with binomial, because binomial starts with BIN. BITS goes with geometric. The only difference between these two is the number of trials is either predetermined or you keep doing it until you get a success. So below are scenarios involving chance behavior. In each case, determine whether the given variable has a binomial distribution, geometric distribution, or neither. Show how each of the BINS or BITS is satisfied. So our example is, genetics say that children receive genes from each of their parents independently. Each child of a particular pair of parents has probability of 0.25 of having type O blood. Suppose these parents have 5 children. We're going to let X be the number of children with type O blood. So let's start with B, binary. This is binary because success would be type O blood and failure would be not type O blood. So our outcomes can be classified into two things, success and failure. Is it independent? Yeah, the genes the children receive are independent, so I is satisfied. Next, we need to determine whether this is N or T. Since the trials are fixed at 5 children, we know the number of trials, which makes this an N. And finally, success. Is the probability of getting type O blood the same each trial? Yeah, it doesn't change. The probability of having type O blood for each child is 0.25. So success is satisfied as well. So we have BINS, which means that this is a binomial distribution. So I'd like you to pause the video, try the next few problems, and when you're done, start playing again and see how you did. Number 1, shuffle a deck of cards, turn over the top card, put the card back in the deck, and shuffle again. Repeat this process until you get an ace. Let W be the number of cards required. So can this be classified into two categories? Yes, success is an ace, failure is not an ace. Are these independent? Yes, since the cards are being replaced and shuffled, the events are independent. The outcome of picking one card will not change an outcome of picking the next card. This is N or T. In this case, we don't have a fixed number. We're going to keep doing this process until we get a success, so that is T. And is the probability of getting an ace the same every time? Yes, since you're putting the card back and reshuffling, the probability of success is 1 out of 13 for each trial. Since we have bits, this is geometric. Number 2, shuffle a deck of cards, turn over the first time cards one at a time. Let Y be the number of aces you observe. Is this binary? Can this be classified in two outcomes? Yes, we have success is getting an ace and failure is not getting an ace. So this is satisfied. Next is independent. Are these events independent? And the answer is no. If you're turning over the first 10 cards without replacing each one at a time, it's not independent. The outcome for the next card is going to change based on what you got the first card. Since this is not satisfied, this can't be either binomial or geometric. Number 3, choose 3 students at random from your class. Let Y equal the number who are over 6 feet tall. Can we classify the outcomes in two ways? Yes, success is over 6 feet tall and failure is not over 6 feet tall. Are these independent? Since students are being selected without being replaced, the observations are not independent. So just like before, we don't have enough we don't have to go any further. We know that this is not binomial or geometric. Number 4, flip a coin. If it's heads, roll a 6-sided die. If it's tails, roll an 8-sided die. Repeat this process 5 times. Let W equal the number of 5s you roll. So are there 2 possible outcomes? Yes, success is getting a 5 and failure is not getting a 5. Are these independent? Yes, the outcomes of rolling a die and flipping a coin do not affect each other. These are independent observations. Do we have N or T? This process is fixed to 5 times, so we have N. And then finally, success, is our probability of success the same for every time? Well, the probability of success will change depending on whether the 6-sided die or 8-sided die is used. So success is not satisfied. Therefore, this is neither binomial nor geometric. So our formal definitions look like this. A binomial distribution is when the count of successes in a binomial setting is a binomial random variable. The probability distribution of X is a binomial distribution with parameters n and p, where n is the number of trials and p is the probability of success on any one trial. The possible values of X are whole numbers from 0 to n. For geometric, the number of trials Y that it takes to get a success in a geometric setting is a geometric random variable. The probability distribution of Y is a geometric distribution with parameters P, the probability of success on any trial. The possible values of Y are 1, 2, 3, etc. So notice here in the geometric, the number of trials is our variable, and that is why Y can only start at 1. We're not going to start at 0 trials.